Let's take a look at a different kind of wave. This wave is called a longitudinal wave, and if we start it, we can see it does go through a similar process as a transverse wave. The difference is we have a different motion in the particles. You can see this is actually the source that's causing my wave, and it's moving left and right, and these pulses are also moving left to right. And if you try to track just a single little line there that represents the matter, you'll notice, and it's easier to see it on the end, that that piece just moves forth and back. It does not actually shift out of position. It's not carried by the wave. So just like a transverse wave, we have a vibration of a medium but not a motion or a displacement of the medium. Now the difference is in a transverse wave, the vibration is perpendicular to the actual propagation of the wave, whereas in a longitudinal wave or a pressure wave, the vibration and the motion are along the same path. Now, just like before, I can increase the frequency, and increasing the frequency will make the wave occur more often. I can change the amplitude. This is a high amplitude wave, and you'll notice those areas that are compressed are really compressed, and the areas that are stretched apart are fairly stretched apart. If I make this a lower amplitude wave, then our compressions aren't nearly as compressed, and our places where it's stretched apart are not nearly as stretched. Now those actually have names, so if I stop this area right here where the matter is stretched out a little bit, it's been rarefied, that's called a rarefaction. The area where it's squished together is called a compression. Now what's cool about a longitudinal wave is that it propagates in a completely different manner than a transverse wave. Remember, a transverse wave propagates because there's a tension between the particles, a restoring force between the particles, and so we can have a wave along a rope that actually propagates because one particle is connected to another, to another, to another. Well, in a longitudinal wave, the propagation is actually more of a pressure difference. We input a pressure over here, and that squishes this together, and then we pull it back, and that pulls it apart. And so we have this high pressure area that is moving through the material. This kind of wave can propagate through a liquid, but a transverse wave can't. And if you think about that, the particles in a liquid don't have that connective force between them like a solid does. So when we squish a whole bunch of these together in a liquid, that creates a high pressure zone, and then they'll rush into a low pressure zone, so you can have an oscillating motion. But if you try to create a transverse wave and you're going to push this particle up, it's not connected to these other particles, so nothing's going to try to pull it back down, and it's not going to try to pull anything back up. So a transverse wave can't propagate through a liquid, but a longitudinal wave can. A transverse wave can't propagate through a gas, but a longitudinal wave can. Now, that tells you right away sound must be a longitudinal wave, because sound can propagate through both liquids and gases. It can also go through solids. So a longitudinal wave can go through any state of matter, but a transverse wave cannot. Transverse waves are limited to solids. Now, we can see that just because it's not a transverse wave, we can't model it like one. So if we consider the average density of the material to be along this line, then what we have here is an area of high density. So I'm going to put that up here. What I have here is an area of high density. I'm going to put it down here. What I have right here is an area of low density. I'll put it down there. And so if I just connect up these points, modeling the density as a function, then you'll see it is essentially just a sine wave still. So we can model a longitudinal wave as a sine wave, and we will, because it's easier for us to think of waves as sine waves, and it's easier to draw a sine wave than a longitudinal wave where we actually have particles of matter being squished around. Just like before, we do have parts on a longitudinal wave, and I mentioned this before, but this area right here where the air has been stretched apart, or the particles have been stretched apart, it's been made rare, is called a rarefaction. Where it's been compressed, that's called a compression. Now, we do have parts of a longitudinal wave, just like we have parts of a transverse wave, so the rarefaction, compression, but we also have wavelength. And just like a wavelength is the distance between any 2 points on a transverse wave that are identical, it's the same thing on a longitudinal wave. So between two compressions, between two rarefactions is a wavelength. Again, frequency is frequency, period is period. Those haven't changed. Amplitude is a little bit different on this wave. A higher amplitude wave means that the compressions are going to be narrower bands. They're going to have higher compressions, and your rarefactions are going to have very low pressure. They're going to be very spread apart. And so we can still model that on a transverse wave. Again, if this is like a density over here, how squished the matter is, then a high amplitude wave has high compression, so it'll be up here and up here. If this was a low amplitude wave, those areas that are of high pressure would still have higher density, but they wouldn't be as high. So we could have a wave that looks like this, and it's fairly high amplitude, and that would be very compressed. Or we could have a wave that looks like this, fairly low amplitude, and so these would be more spread out here, and there wouldn't be as big of a difference between a compression and a rarefaction. So longitudinal waves, different than transverse waves because the vibration of the motion is parallel to the vibration or the propagation of the wave, and also because the force is due to pressure differences rather than a restoring force from tension like in a transverse wave.